UCSD ECE 111 Lecture 3 Set 2, various types of memory that we will be covering in the class. The main two distinctions in the memory is a random access memory, or RAM, which is typically used to indicate a volatile memory, and then the read-only memory, or ROM, is used for non-volatile memory. This, as I mentioned a little earlier, this may be a misnomer because even some of the memory types that are called non-volatile, for example, a flash memory, you can actually write to it as well. It's just the asymmetry between the reading and writing that defines this notion of read-only and write-only. For example, when you write to a flash memory, it's going to take a lot more time and a lot more energy than reading from it. So it's in effect an asymmetric type of memory, which is called a ROM. We can read from it easily, but not write to it as easily. The random access memory is typically a volatile piece of memory. When you say a RAM, this is historical because RAM was a type of memory which was invented where you could use an address decoder to access any of the bits in random order. This was as opposed to when old times they had this tape-based memories that were sequential. They're using those, but the main memory in the computer is usually a random access memory. In particular, DRAM arrays are usually a huge part of the memory in your processor. For example, in general-purpose processors, the SRAMs are typically the cache, which have limited sizes, and the DRAM is the main memory of the processor that we usually read and write to. There are different types of RAM, DRAM, or dynamic access random access memory, which is, as I mentioned, the bigger part of our memory in the computer is that. The static memory is just a different way of storing value to the memory. The DRAM uses a capacitor, and SRAM uses cross-coupled inverters. Let's go through the structure of these two and see how they differ. So coming back here, we have the stored bit and we have the word line, bit line. If it's a DRAM, then what happens is we are going to have a switch that is saying if this word line and bit line are, this is the gate of a transistor and this is basically the channel. And then this channel, which is a switch on-off switch based on the value on this word line, is controlling a capacitance here. And the value stored in the capacitance is 0 or 1. So if this is 1, the capacitance is basically disconnected from the ground. If not, it is connected to the ground. And now one thing to know is that in actual physical setting, what happens is that they don't go and use a separate piece of capacitance as a discrete element here, but usually the capacitance of this gate to source of this transistor is used to store the values for in DRAM. Now SRAM is a little bit different. If we look into the structure of an SRAM, what happens is that we have these, basically, instead of just one bit line, we have both bit line and the inverse of the bit line. And these two are basically controlled by a switch that is connected to the word line, similar to this case. But here, the main element that stores the values of the memory is a connection of two back-to-back inverters. So if you remember from your logic design course, this is a positive feedback loop, basically a circuit in a metastable state, meaning that when we have this positive feedback loop, such as for example this one is 0, this one is 1, then it comes here 1 and 0. This is very stable. Now, if we want to change the value here, what we need to do is we need to pull up one of the connections, to get a 1. If you want to change it to 0, then we need to pull it down all the way to disrupt this positive feedback loop to get a value stored here. But perhaps more importantly here, what we see is that here, to store a bit in the memory, we had a one transistor construct. transistor. And then here, the CMOS NOT gate has 2 transistors in it. So 2 and 2 is 4, and 1 and 1. So we have a 6 transistor structure to make this other circuit. So let's go back to the memory array we took a look earlier here. If, for example, we are using this 4 by 3 array, which means 12 elements. In the first case, we are using 12 transistors. In the second case, we are using 72 transistors for implementing this. So there is a trade-off between the area and the performance of these elements. However, every time we have a DRAM, because the values in the capacitance they tend to drift, we need to keep updating the values. That's why it's called DRAM, dynamic RAM. We need to keep updating the values every few fractions of a second to make sure the values are stored refreshed. They don't drift, but SRAM, once you store it, it is stored there. So there is this trade-off between this 2 pieces of the memory. One thing we could do here is if we were showing this ROM or DRAM or any kind of memory, we could use the values for the addresses on one side. So the address decoder is decoding things to 4 things, and then you could use the value stored. You could represent it with these dots. So every time we have a 1 stored, then we have a dot here. No, we don't have a dot here. If we have a dot, means that this bit cell is contained 0. And then, if there is a 1, we kind of disconnect the dot. So for example, so here, what happens is that every time if you have a lookup table, we could represent it in this dot notation. Every time we have a 0, this dot is disconnected. If there is a 1, that means that this dot is connected in this array. And this way we could show a value stored in a storage. Now let's take a look how we could use this to really make logic out of memory.